Good afternoon to all. Myself Urvashi Jhamukia, PhD Research Scholar at Department of Physics, Saurashtra University, Rajkot. I heartily welcome all of you on the platform named Vigyan Yatra, a travel for scientific Indian minds toward Vikshit Bharat, a series of conferences session for 4th to 15th March 2024 and is jointly organized by Department of Physics, Saurashtra University, Rajkot, Vigyan Gurjari, Gujarat Prant Unit of Vigyan Bharati VIBHA, and GUJCOST, Department of Science and Technology DST, under Gujarat Vigyan Sammelan GVS 2024. We are honored to have with us the invited guest for today, respected Dr. Indrajit Patel, Principal Birla Vishwakarma Mahavidyalaya, Vallabh Vidyanagar, Gujarat. We are extremely grateful to our Chief Patron, Professor Nirambari Dave Ma'am, Honorable Vice Chancellor, Saurashtra University, Rajkot, Patrons, Professor Chaitanya Joshi, President Vigyan Gurjari, Gujarat Prant, Professor Girish C. Bhimani, Dean Faculty of Science, Saurashtra University, Rajkot, and Dr. Narottam Sahu, Honorable Advisor and Member Secretary at GUJCOST Gandhinagar, and our co-patrons Dr. R.G. Parmar, Registered Saurashtra University, Rajkot. I heartily welcome the eminent speakers of today, Professor Krushna Mavani, Professor, Department of Physics, Indian Institute of Technology, IIT Indore, and Dr. Mukesh Ranjan, Scientific Officer G, Institute of Plasma Research, IPR Gandhinagar. I also welcome the session chair, Dr. Pankaj C. B. Thakur, Professor at Department of Physics, Veer Narmad, South Gujarat University, Surat. The conveners of GVS 2024 Rajkot, Professor Nikesh A. Saha, Head of Department of Physics, Saurashtra University, Rajkot, and Professor P.N. Joshi, Secretary at Vigyan Gurjari, Saurashtra Prant, Rajkot. The event coordinators, Dr. Rupal K. Trivedi, Associate Professor, Department of Physics, H&HB Kotak Institute of Science, Rajkot, Dr. David B. Dhruv, Assistant Professor, Department of Physics, Saurashtra University, Rajkot, and Dr. Piyush S. Solanki, Assistant Professor, Department of Physics, Saurashtra University, Rajkot. Moving ahead, I request my fellow researcher, Ms. Bharvi Hirpara, research scholar and SRF of DAE-BRNS research project from Department of Physics, Saurashtra University, to welcome and introduce us to our today's guest.
Thank you, Urvashi. I now take a chance to introduce our guest of honor and co-patron, Dr. Indrajit Patel sir, Professor and Principal, Birla Vishwakarma Mahavidyalaya, Engineering College, Vallabh Vidyanagar. He is a PhD in structural engineering with 40 international publications, 13 national publications, and 26 years of teaching experience, 4 years of research experience. He has also guided successfully 4 PhDs and is a recipient of 11 awards in his field. We are very honored by your esteemed presence in today's event, dear sir. I also take the honor to invite today's session chair, Dr. Pankaj C. Thakur sir, professor at Veer Narmad South Gujarat Universities. He has got a wide research experience in the field of theoretical condensed matter physics. He has got 77 international publications, teaching experience of 24 years, and he is also a life member of Indian Physics Associations, Indian Liquid Crystal Society, Indian Association of Physics Teachers, that is IAPT, Material Research Society of Indian, MRSI, Associate Fellow of Gujarat Science Academy and International Disordered Systems and Associate Society, that is India. He is also actively participated as a member of syllabus designing committees and a member of board of studies as well as the research advisory committee. We are extremely graced by your presence of today, sir. And I now have hand over to session chair, today's session chair, Dr. Pankaj Thakur sir, for further coordination.
Okay, Bharat. Now, on behalf of this Vigyan Yatra, I welcome today's speaker.
Sir, we are not able to hear your voice.
Hello. Yep.
Okay, namaskar, one and all present on this digital platform for a flagship event of Vigyan Yatra, embarking the importance of science, technology, engineering, and mathematics to a nationally and internationally recognized and appreciated platform of Vigyan Bharati, popularly known as VIBHA. Thought process being initiated at IIC Bangalore during 70s, and the further discussions and brainstorming session gear up the Swadeshi science movement during those days. And during 90s, particularly 1991, at Nagpur Bethak, this particular organization, VIBHA, came into the true philosophy, thought process, and imbibing the heritage of our India, I would say rather Bharat, in varieties of the domain, from a single thought. In those days, it has now penetrated to more than 26 states. Another 5 to 6 states are under connection to spread the aims and objectives of VIBHA to the state functionaries, state organizations, and different IAMs of VIBHA. It was clearly decided about the fundamental aim and objectives of VIBHA to work for the cause of the Bharatiya heritage with a harmonious synthesis of physical and spiritual science to nourish an individual to the mass, to the society and nation at large. It was focusing on rejuvenation of Swadeshi movement in the age of science, technology, engineering, and mathematics. How it brings the revolution for the holistic development right from a tribal to rural to the metros of our Bharat. To enlighten and gearing up this movement of Swadeshi science and technology, right from Ayurveda to Siddha to meditation and yoga, organic agricultures, Vastu Vidya, forestry, astronomy, environment, engineering, and beyond this, to the varieties of the activities by the state organizations or at the central, that is VIBHA, in terms of Vidyarthi Vigyan Manthan, World Ocean Congress, co-host of the Indian National Congress, VIBHA Vigyan Sammelan, India International Science Festival, and recently we have engaged in Azadi Ka Amrit Mahotsav, right from a person to the nation. Vigyan Bharati work for the holistic connectivities of the ancient science to the modern science. It deals with the science education programs, science outreach programs, empowering the youth in a domain of STEM, organizing science fair right from the school level to the institutions, to the colleges, to the universities, as well as encouraging effective communication in scientific concept under a title of the science communication. Science does not mean a conventional physics, chemistry, biology, or computer science. VIBHA has spread its wings to address the domains of the emerging areas, but keeping the heritage of ancient India in the center. Nowadays, people talk about the computer science, earth science, astronomy and astrophysics, neuroscience, nanotechnology and genomics, material science through nano and particle science, and one of the most important needed, that is the environmental science. When we transfer ourselves from industry 1.0, that is the conventional mechanical and electrical engineering or science, industry 2.0 with innovation of some electrical and electronics science. Then industry 3.0, again we have entered into IT domain and computer science and information science. We are in the era of industry 4.0, where we talk about the cognitive applications and the features like artificial intelligence, machine learning, rapid prototyping, deep learning, and much beyond this AR and VR technology. But we look ourselves in the history of ancient India. All these things have been written in black and white through our scientists, our astrologists, our people who are engaged in Ayurvedas, Aryabhat, Bhaskar, Varahami, all these people. Even we talk about the Dwapar and Treta Yuga, the missile technology, the planes, the artificial intelligence, the deep learning, all these things have been put in paper in black and white in one or other form. So it is the role and responsibility of this VIBHA, which is engaged in connecting this Asian science and Asian technology to this modern technology. We also talk about space exploration, brain science and brain mapping, genetic and gene editing. Also, again, the need of the day, that is renewable energy to preserve our Mother Earth. There is the sustainable development, sustainable material, and the green material along with the smart materials. So all these things are the need of the day, and VIBHA is taking a keen interest through its different IAMs, how we can propagate all this technology, keeping in center our ancient technology. VIBHA always look forward to honor and appreciate our great scientists who have put their life to connect with the ancient science, with the modern science. Right, we talk about Aryabhata, Varahamira, Brahmagupta, Susutra, Chanakya, then Charakrushi, then again Vedbhaga, Aitreya, Bela, and to our recent scientists who have given a new dimension to the science and technologies in India, Dr. C.V. Raman and Srinath Bose, J.C. Bose, APJ Abdul Kalam, Vikram Sarabhai, Homi Bhabha, then Venkatraman Ramakrishnan, Sri Chandrasekhar, and much more. So all this birth anniversary of the scientists are being celebrated by organizing lectures, lecture series, competition. We should not forget Ramanujan so far as mathematics is concerned. So Ramanujan Day is celebrated, and along with the different bodies like AICT, UGC, and other councils, along with VIBHA, always try to see how best we can imbibe the core value in the youth, how you can interact with the educational bodies to have their syllabus in context to our ancient and modern science. So really this Vikas Yatra will put a new paradigm in the journey of VIBHA as well as Vigyan Gurjari. This is as a part of the Vigyan Gurjari and Vigyan Sammelan. So Sammelan recently organized, and our Vigyan Gurjari particularly is very active when we see about the other state. So Gujarat is model everywhere. So VG is also model for other state, and I am happy that Department of Physics, Saurashtra University has taken this particular initiative to invite the experts, the researchers from all over the country who are dominating their time for the research and giving a real, homage to our scientists, our heritage. So I end this way. I am thankful to the organizers for giving me opportunity to meet all of you. Bharat Mata ki Jai, Vande Mataram.
Thank you so much, Dr. Indrajit Patel, sir. I now invite Professor Pankaj Singh Thakur, sir, Professor Veer Narmad, South Gujarat University, as the session chair, and hand over the session to him.
Okay. Thank you, Hirpara. On behalf of this Vigyan Yatra, I welcome all of you. Now, we start the session. Today's speaker is Dr. Krushna R. Mavani. She is currently Professor of Physics at Indian Institute of Technology, means IIT, Indore. The most important thing is that she is an alumni of Saurashtra University. She did her PhD in the year of 2003 from Saurashtra University. Then he moved at TIFR for her postdoctoral fellowships. After that, she also moved to the Japan in the Osaka University as a postdoctoral fellow. And after that, he is currently working as Professor of Physics at IIT Indore. Today's topic, spintronics, a new route of futuristic technologies. Madam, I invite on behalf of the Department of Physics of University, GUJCOST, Vigyan Yatra,
Thank you.
talk.
Thank you, Dr. Thakur. So, yeah, as rightly said by Thakurji, I am alumnus of Saurashtra University, and it is really my pleasure to deliver a talk at the university where I have studied in the past for several years. Since I have been there for a long time, I know many of the organizers quite well, and I thank them for this invitation. It actually really is a pleasure for me to deliver this talk here. Presently, I am working in area of sprintronics, and before that, I have been working in many other different areas. And now we are also developing other techniques in the laboratory. So these are some recent results I'll be sharing along with the idea of spintronics and what are the futuristic technologies which we can develop using this material. So let me share my slides here. Okay, I need to open my presentation, just a minute. Okay, I'll open my presentation and again continue, just a minute. Can you see the slides yet? Okay. Window. Somehow I'm not able to share the PPT slide here.
You please open the PowerPoint and then there is arrow upward present now. So your screen will be loaded.
I have PowerPoint present.
Yeah, so open your
Slides
PowerPoint
from
presentation and then share the screen. That is arrow upward.
Yeah, I can see.
Bottom.
Yeah, thank you. That is useful. Wait a minute. Share. Maybe I can try enter screen here, but it's not working. Yeah, but then I can see on. Let us see. Let us see. Can you see something now? Now, if I open the slides, can you see?
Now slides are visible. Now you go to the slideshow.
Yeah, now I know. Let me start from the beginning.
Yes.
Yeah, can you see now?
Perfect.
Yeah, so this is my topic, as you know, spintronics, a new route to futuristic technologies. So basically, let me start with very fundamental idea of spin and charge, how they are originating from electron. You know that electron is orbiting around the nucleus, and you have a spin momentum. The spin is rotation of electron around itself, and then this spin, whether right-handed or left-handed, will generate spin up and spin down states. So remember that spin has two state with respect to the up and down orientation of the spin, and the charge. See, electron carries charge. You know that when it is moving in a medium, we call it current when many electrons are moving in one direction, right? Now, when the charge is associated with electron and spin is also associated with electron, it is also having orbital motion. So there is a spin orbit charge correlations which we generally harvest for the applications in this area of spintronics. So let me briefly tell you my overall plan of presentation. I'll be starting with introduction to this area of spintronics. Then what kind of technologies, different variety of technologies are now possible with this spintronics, and we'll be discussing only few selected ones here which are kind of promising for the futuristic technologies and which will kind of very recent predictions are made for certain materials. Then there are some results from my laboratory on half metallic double perovskite thin films. These perovskites are actually very promising for spintronic applications. How we can manipulate the properties for our applications and all we'll discuss. And these results from my laboratory I'll share with you. So why spintronics? As I the problem is that now you see all the appliances in surrounding, they are getting smaller and smaller day by day. Your computer, your mobile phone, right? So they are actually smaller in size, and not only that, they are increasingly using ICs, more and more ICs in the appliances. So what happens? A lot of power consumption and a lot of heat generation, and that is becoming a major problem nowadays. So that is one issue why we should look forward to advanced technology. And as an alternate solution, we have spintronics devices which offer possibility of enhanced functionality with lower power consumption and very higher speed, okay, compared to what we have today. So if you harvest only electronic functions, the applications like field effect transistor, PN junction diode, random access memory in computer, etc., can be actually this electronic function have magnetic ordering. You can have hard magnets where you can use it like a needle in compass or memory in hard drive, like that. Now, this is like the word spintronics. It happens to be like spin plus electronics because we are also using spin functions in addition to some electronic functions. So that is why spintronics, and that can be like new phenomena like giant magnetoresistance can be used to sense the memory. Then you have magnetic random access memory device. Okay, it doesn't consume so much of power, and then you have spin polarized current in field effect transistor. So already some existing electronic functionalities will be using in addition to spin. So what are the basic principles behind this kind of spintronics? As I told you, there are electrons and they have spin up and spin downside. Now let me use a pointer here if I can see. I hope you can see a pointer, laser pointer here. So depending on the rotation of electron in opposite direction, it can have up and downward momentum. Now, if you are passing electrons through a medium, it is called current. Spin unpolarized current means it is randomly oriented spins. However, in picture you can see only two orientations, but they are actually randomly oriented, and the net polarization of electrons is zero. Okay, so these kind of currents we see in day-to-day life today, and we use that in today's electronics. But if you have spin polarized currents, all the spins are aligned. If it is 100% polarization, they'll be aligned in one direction. Okay, so that is called spin polarized current. Now you can harvest the spin functions as well in addition to electronic functions. So this is the basic idea behind the spintronics, and it is information carried by orientation of spin rather than charge or in addition to the charge. Both are true. Okay. And when the system is switched off, in some cases, the materials have a memory which can stay and doesn't go away. There are two types of memory, volatile and non-volatile. You should know that. Okay. So now first thing which we start with is giant magnetoresistance. So this discovery was made by two scientists called Albert Fert and Peter Greenberg. In 2007, they were awarded Nobel Prize for this discovery, and that is the observation of giant magnetoresistance in a layered, thin structure. In layered, thin structure, the spin exchange actually interferes with the electronic hello, yes. Yeah, so this discovery was very important, and it has set the foundation for the area of spintronics. You can see that. So the principle is like that there are two layers. you can see in figure B here, I have shown the spin orientation of three different kinds. In first one and last one, they are like ferromagnetic exchange interaction. In the middle one, you have antiferromagnetic exchange interaction. But here, basically, this is just to show that in case of ferromagnet, if it is ideally parallel in with with each other, so what do you see? As you vary the external magnetic field which is applied to the layers here, the resistance value is low. Okay, and what happens is, because it is ferromagnetically aligned, there is a spacer layer in between. It is very easy for electrons to tunnel through because they carry the same type of spin. But when these material they are anti-parallel, what happens? They actually rise in the resistance. You can see the vertical axis is actually rising up and showing a peak, and then again going down as you change the magnetic field again. So this is basically like hysteresis. You can see this is your zero here in the center. If you increase the magnetic field towards higher side, you can compare with the magnetization curve shown here. As the spin is getting more and more parallel, magnetization is rising. At the end, you all know that the magnetization gets saturated at a certain value of external magnetic field. You reverse back, it may, in a soft magnet, it will come back to the same path. If it is a hard magnet, you will see a magnetic hysteresis. Okay, so this will, I am not showing both the curves here for rising and falling. I am showing only one curve while rising the magnetic field. And then if you see the negative side, you can symmetrically see that the curve is showing saturation of magnetization in the negative side as well. So similarly, resistance on both the ends when it is saturated magnetization is very low. So these to vary the resistance, and it is called magneto-resistance, because on application of magnetic field, as the spin align parallelly, the resistance reduces drastically. This is the first discovery made in giant magneto-resistance multilayer of iron and chromium. What they observed is that in case of their multilayer, the chromium thickness was changing from 9 angstrom to 12 angstrom to 18 angstrom. Here, on the x-axis, you can see magnetic field variation in positive and negative side. On y-axis, you can see the resistance. This is the ratio of resistance when in absence of magnetic field, which is H is equal to 0. So it is 1 here because you start with 0 magnetic field, and as you increase the magnetic field, it is decreasing because of ferromagnetic exchange. Now, these kind of result when thickness is changing and the magneto-resistance is changing because of the thickness. There is a thickness dependence. That is because of the RK-KY type exchange interactions. These are not normal, near neighborhood direct exchange. It is called indirect exchange interactions, and they depend on the distance between the two charge carriers carrying the spin. If you vary the distance, I have shown one oscillatory function here. This one is time dependent, but assume that this is x actually. This is the distance on x-axis. As you vary the distance from one spin to another, so it is ferromagnetic exchange interaction here. As you vary distant goes to anti-ferromagnetic exchange, then ferro, then again anti-ferro, and the momentum is decreasing. So this is harvested for actually observation of giant magneto-resistance. Now that was very complex to understand. It was just a bilayer system when they observed it, only iron and chromium structure like this. So you have a spacer layer introduced between two magnetic layers. The spins are aligned parallel. If magnetic field is applied, they are first magnetized. Then this is the situation. This is just to understand how it works. Okay. So you have one electron. Suppose it is a positive half spin. It means then spin is up. it will go through easily without having any scattering at the interface. If it is pinned down, because it is reverse of this orientation, it will be having multiple scatterings at the interface. Maybe it will not even pass through the multi-layer. Okay, this is the situation. It is, it can be conceptualized in a kind of two channel resistance circuit, if you can understand this very easily. Here you have larger R, okay, and then this pin, if it is negative, it will have more scattering at the interface. It will having more resistance, right? Another channel which is operative only for spin up, it will be having lower resistance value. Similarly, this can happen if it is anti-ferromagnetic alignment. The scattering can take place at interface for both the types of spin alignment, right? Which can be understandable using this kind of diagram where you have combination of larger and smaller. So there is another phenomena, colossal magnetoresistance. The values of this magnetoresistance are quite comparable to giant magnetoresistance, but the principle is slightly different. In giant magnetoresistance, you had multiple layers, right? Here you have just kind of chains of manganese, oxygen, manganese ions. This manganese, oxygen, this arrangement across the crystal structure will be actually participating in the charge conduction. So here I have shown you one, ideal structure of LaMnO3 type of manganite perovskite, where you have lanthanum in the center. These are manganese ions, okay, and these are oxygen ions. So you can see one octahedral forming here in the single crystal. So if single crystal unit cell is given, you can understand this oxygen is also part of actually another unit cell on top of it. So that is why this chemical stoichiometry looks like LaMnO3. La is 1 here. Manganese, because of sharing, actual contribution is 1. So that is why La, Mn and oxygen contribution, if you count with sharing and all, finally it will be O3. So if I see just one octahedral, MnO6, it is called MnO6 octahedral, just taking one manganese in the center and oxygen 6 ions here. So this is the ideal structure. Okay, now manganese here in this case, lanthanum is trivalent ion, manganese also trivalent ion. Manganese is also known as Yarn-Taylor ion. It is Yarn-Taylor and its electronic configuration is like this. Maybe you know already there are, if you take 3D orbitals, there are EG types of spin, T2G types of, EG types of orbitals and T2G types of orbitals, right? If you may know Hund's rules and your final electronic configuration in case of manganese 3+. Okay. Now, because of crystal field effect in surrounding, it will further split up like this. So these are known as T2G orbitals. They are TXY, DXZ, DYZ. Okay, in EG orbitals, they are slightly higher energy states. And electrons fill up like this and show the structure, because it is a lattice and electron are actually correlated. You see a elongation along y-axis of this structure, and in AB plane it is called, actually if I call A, B and C lattices, then C is elongated and AB plane is contracted. So these kind of this particular situation can be actually manipulated by application of magnetic field. What happens is, this was the pure LaMnO3 perovskite. When I dope lanthanum, when I dope calcium at lanthanum side, okay, you substitute maybe close to 25%. What do you see here? So you have manganese converting into 4+ state. You have manganese trivalent state initially. After divalent doping, it converts to tetravalent state. Okay, so you can see 25% manganese ions with the tetravalent state here. And as you apply magnetic field, what happens, I would like to explain here as a double exchange scenario. See, initially your manganese was just 3 plus 3 plus, but when they are like MnO, Mn chains with manganese trivalent and manganese tetravalent, what happens is manganese tetravalent having vacancy here for electron. Now, oxygen 2p orbitals, they overlap with 3d orbitals of manganese. So this electron can have, double exchange. Once there is exchange with oxygen 2p orbital, and then next again with Mn4 plus. So basically this Mn3 plus and 4 plus is a kind of dynamic state. While electron conduction is happening on application of electric field, this when electron hops from here to here, this may become this will become 3 plus and this becomes 4 plus, right? So there is another vacancy here. So manganese on the other side can transfer the electron. So this is the scenario which is called Zener double exchange. Scientist called Zener so proposed it and explained it. Spins are parallelly aligned. So this scenario is possible when you have ferromagnetic spin, okay, ferromagnetic exchange. So when more and more spins align, this more and more double exchange of charge carriers is possible. So conduction increases and your resistance decreases. So as you apply more and more electric field from 0, this is H is equal to 0, 1 Tesla, 2 Tesla up to 4 Tesla. So this largely decreasing resistance is called colossal magnetoresistance, and since it is decreasing, it is called negative magnetoresistance. Now there are some techniques and terminology which are recently observed. This was the and all. Few decades back they started, and many papers are available on this kind of materials where they observe this kind of phenomena. Now these are something recent techniques here which I would like to briefly discuss. Another one is this tunneling magnetoresistance. This can happen in even layered structures. So you can say that in GMR case is a bit of tunneling only, but here let me explain you in detail. You have a barrier. Barrier is potential barrier between two magnetic layers. This potential barrier is actually produced by one spacer layer. Okay, this layer is conducting but may not be having that much, it is very high in resistance. So it's very thin. So the electron can tunnel through the barrier, okay, when you apply magnetic field. So let us understand there are two situations given here. Okay, first of all, TMR ratio can be defined. So TMR ratio is given like this: P1 and P2. P1 and P2 are kind of polarizations associated respectively with first layer and second layer here. Okay, so how do you define polarization? Polarization can be like number of majority charge carriers minus number of minority charge carriers. Now don't confuse it with semiconductor physics. I'll tell you what are majority minority here. Okay, and divided by total number of charge carriers. In majority carriers are the electrons having spin up or spin down. So the types of carrier is same. Okay, but the spin up electrons are carrying the charge or spin down electrons are carrying the charge. Which one is dominating? Because see, ideally you may say it is spin polarized current, but there are some minority carriers which doesn't have the spin alignment same as other electrons. Majority spins are aligned, some spins are not aligned. Okay, so they are like minority spins. So you generally talk about two channels, spin up and spin down channels. That's why this terminology is slightly different here. It's not like holes and electrons, majority charge carriers in a semiconductor. Okay, so this is the spin polarization. If you want to define, this is the idea you can use, and then use this equation to find out the TMR ratio, to define the TMR ratio. Now here you have two layers which align ferromagnetically. Now since it is FM1 and FM2, the materials are different. So this is the spacer layer, and look at this density of states given here, and this is the Fermi level, and you have spin down states here shown as majority, you see, and spin up states shown as minority. On the other side here also it is similar, spin down is majority, spin up is minority charge carrier. So spin down up will go to spin up here, and spin down after crossing the barrier can acquire this density of states. So now another thing is this A1 and 1 minus 7. A1 is you can say, suppose whatever percentage or number of density of states here, and 1 can be 100% or whole number of carriers, minus 7, rest of them are sitting here as minority. Okay, so this scenario is understandable now. When you apply external magnetic field here, what may happen is, you see they are spin up now. You assume that applied magnetic field is in this same direction, then what happens? Then spin up, more and more charge carriers with spin up condition should be participating in this tunneling, right? And in other case, what happens slightly different. So here what happens, as you increase magnetic field, resistance changes because more carriers with spin up condition will be participating. So there is a tunneling, more and more charge carriers will tunnel through the barrier and resistance will change. While this may decrease, spin down state, lesser and lesser number will be possible because of application of field. Now you have another scenario with spin up and spin down condition here. Here your majority is spin down, in the other side it is reversed. Majority is spin up, okay, because of the situation in two different layers. Now here also if you apply magnetic field, naturally spin up will participate more here. Okay, more and more spin up electron should jump up and go to this state. So here this case the current value produced is slightly lower, but this kind of tunneling is possible in ferromagnetic as well as antiferromagnetic materials. Now this spin transfer torque. So this is spin alignment because of external magnetic field. Okay, now here we'll be talking something because of current, how you can actually spin can be transferred from one layer to another. In this case, again I have shown you two different scenarios. It is used for magnetic switching. This kind of technique is used for magnetic switching, where here fixed layer is on fixed. M fixed matlab means magnetization is fixed. It is not free to move in any other direction. Okay, you have aligned fixed magnetization for one layer. Now you have a non-magnetic layer. It just actually helps the conduction, and it is thin in layer, electrons can tunnel through. And there is another magnetic material where M is free to move in any direction. Now suppose your current is flowing from here to here, it means your electrons are flowing from left to right, opposite direction, right? So electrons are entering from this layer, okay? So they acquire, because of influence of this, now see here magnetization is acting like magnetic field, internal magnetic field, which will influence individual electron traveling through the layer. So as they travel, they now have some kind of spin polarization. So they go through non-magnetic layer with the same spin polarization and enter here. Now here situation is slightly different. Because of magnetic moment in another direction, it applies a torque. This is a vector showing a torque, maybe torque up and torque down with respect to each other. So this torque is applied, and that's why the spin straightens up here. Okay, so this is shown only for one electron, but that is the example electron here. You have this situation for many electrons. So finally, the electrons coming through this multilayer structure will have a spin, you see. So actually spin transfer has happened, and these electrons which were unpolarized now kind of having some net polarization at the end, right? Now here in the reverse process, what happens, let us try to understand. Also, there are some equations given here. The spin polarized current contains an angular momentum which depends on this equation here. These are all traditional notations, and it undergoes a spin scattering process also. Remember here, spin angular momentum is conserved. That is most important part, because if it is not conserved, this torque effect is not possible. Spin angular momentum is conserved and it is transferred from without having any such loss. So let us now see the reverse process. Here electrons entering from the right direction, so already it is free magnetic field, it is already free to move, and what happens is more and more electrons are having they pass by, and there is a torque, reverse torque applied here, and because of magnetization, under the influence of magnetization or whatever magnetization it may be, it will acquire a spin. Okay, and okay, you just refer to this path first, and there is a returning path also. So we go with a spin alignment into non-magnetic layer, and there again you have different spin alignment which doesn't change. This is fixed. So what happens is, because of conservation of spin momentum, there are some electrons which get influenced by this spin alignment, go through having that spin alignment of M fixed. Okay, and there are other which are reflected back. They are reflected back with a little change in the spin alignment, and then kind of you see in it's like you can say optical waves, when they get reflected back, there are actually uh, phase change in the optical waves. Similarly, if you see, they are tunneling through, they are quantum mechanical phenomena involved. Okay, so then they are reversing back, and you have a torque generated in the opposite direction here. Okay. They can't go through because of the scattering process at the interface. So what happens here, in the reverse direction, you get this kind of spin alignment. So here you have spin up kind of situation, and here slightly different. The spin transfer can be used to switch the magnetic spin of the current. Now there is another technique called rest track memory. This is very recent, and many predictions have been made by IBM. Actually, I think 2019 they have started predicting this kind of 3D memory for computers. So here, what happens is, actually domain wall moment is present. Rest track memory was given. This name was given because initially the design was actually looking like a rest track. Okay, but now the design is slightly different, so nowadays people are calling it domain wall memory, because the domain wall moment is involved here. So in the recent design, one of the example I'm showing here, there can be many more designs possible. So there is a nanowire here. Nanowire means kind of 50 to 100 nanometer thick. Okay, so what happens is, you can have positive current pulse here, that is again spin polarized, and you have information stored as magnetic pattern like this. Actually, it can be spin up and spin down domains. Okay, orange and blue, and then there are some write heads and read heads which are stick on a chip here, and this is standing on that. Okay, and then bits means these are the spin up and spin down domains, they move left and right depending on the direction of current. So suppose you have current entering from this domain wall movement, because of that these domains can move as shown by this arrow. They can move from this side to that side, other side. Okay, while they are moving, what happens here, there is a read head which is magnified and shown here, small reading head is there. As domains pass through this head, it can read it. Okay, now what happens in the current hard drives, the whole drive is moving, whatever you are using, small disk or whatever it is, whole disk is moving, To move that disk, the power consumption is quite high. Here you are not moving anything. You see only domain wall movement is happening, which doesn't need that much power. So it is not only faster, but also it consumes very less power. Okay. Now this is right head as magnified. I think this is the right device. So right head, you can say. The current pulse as shown by blue arrow generally goes through when you need to write something. Okay. Suppose this red is one domain, you want to change it to blue, then you pass a spin polarized current and switch it to another direction. So this is writing actually. This is how you write memory, right? They are binary states, up and down. So you switch it from up to down. You are writing the memory actually. Such kind of actually designs are stacked in a kind of chip actually, but it is 3D. It is called 3D memory because it is no more two-dimensional like a plain thing. It is rising up as a thickness. I mean this length of the wire is also one dimension in the memory. So this actually this picture is taken from one nanoscale research letter paper. So very detailed discussion is given here. Another thing is magnetic skyrmions. This skyrmions is not a condensed matter term actually. It is coming for high energy physics. Something like 50 years back, people predicted particles like skyrmions in high energy physics. However, these are quasi particles. They are not like proper particles, but they are quasi particles because they are called particles because you can actually move them, create and annihilate them, manipulate them like that. But like as if a particle state is there. So there is how do you define it? A small spin, swirling vortex-like structure in a magnetic. It can be called a magnetic skyrmion in a medium. So now this medium is always a magnetic material, and that is generally non-centrosymmetric magnetic material where you can generate this kind of topology. And this was theoretically predicted, but experimentally it has been demonstrated in 2009 only. If you want, you can refer to this paper which was published in Science by these authors, where the title is Skyrmion lattice in a chiral magnet. Chiral magnets generally have Zylosensky-Moria interactions. Those who are working in the area of magnetic perovskites may know about Zylosensky-Moria interactions. They are like spin spirals, the spin alignment as you travel across certain distance, they spiral, okay, and in a wave-like fashion they go. So these kind of magnets can have this kind of vortex-like swirling particles, and depending on the topology of this spin here, you can call them skyrmions and anti-skyrmions, and now there are other names also given to this. And these are simulated figures, okay. So some this parameter shown here, they I think define the direction from where you start up and down, and as you move out radially from center to outside, finally this is changing, it is rotating. So this change is in plane, or maybe this change is happening out of plane, and it is starting from zero spin and then entering into full ferromagnetic like spin alignment um, at the periphery. This kind of skyrmions are present. So these three are shown in a kind of 2D sheet in a simulated figure. Now these are kind of 3D skyrmions which are predicted to happen in some materials, and they happen to be like this, where you have different type of spin alignment changing like a sphere pattern on a sphere. So this is yet not observed, I think, experimentally, but even optically you can tune these skyrmions, and many more research papers are being published in this area. There is one more phenomena called spin resonance. Now, this device here is just to understand, this is just one design. You can design your own device the way you like, but here one classic design is given. A schematic is multi-layer. Okay, it is V2O3 here. You know, this is a oxide material, but on top of that you have magnetic layer like nickel, and then you have one a permalloy. Permalloy is combination of nickel and Fe in certain ratio, so it is called permalloy, and the symbol is Py here. On top of that, you have some electrodes like made based on platinum, and you have a source here, and you have electric ground, and okay, so anything else? Yeah, so this is not to the scale, by the way, in the figure. This is magnified and shown here for our understanding. Now, what happens is when you pass the spin polarized current, it excites the spin dynamics in a magnetic material. These are the simulated lines which actually show the current, simulated current passing through the juncture here, which is very small. It is SEM image of that. You can see the nanometer scale here in the SEM image. So the density of lines actually show the density of current here in the middle of it. So because of it, this intense currents passing through the juncture, there is you can actually excite some spin dynamics when it is going through some kind of magnetic transition. And these magnetic excitations can lead to variation in the resistance, and when resistance is again changing, you can detect it electrically. Okay, so these kind of devices can be used in neuromorphic circuits actually. And those who know, neuromorphic is actually a simulation for our in how brain works, and all such kind of areas are there in biology. It's kind of biophysics. So there you can use such kind of devices, simulated devices, and then you can design it and actually play with it, design in simulation and see how it works for neuromorphic designs. So we have seen certain varieties of applications of spintronics, and see, there are two types of things shown here. One is mode type of materials, which can be used for spintronic memory devices, and there are Dirac type of phenomena which you can harvest. You know that mode type, maybe it's more like you have seen mode transition. It is like metal to insulator transition. Because of Coulombic repulsion and intense electronic interaction, sometimes they are insulator. Okay, as you lower down the temperature, you can see transition to metallic states. So if you go by band theory, they are supposed to be metallic, but they don't conduct, because of, and that cannot be explained by band theory. Okay, so that is a the phenomena given by a scientist called Mott, and he made this. He could explain actually very successfully these metal insulator transitions. So the many oxides actually show very intense, strong electron interactions and show metal insulator transitions, and they are actually practically possible to make spin memories out of them. So as I showed you, restrict memory, MRAM, hard disk, GMR or TMR can be used here for variety of things. Then on the other hand, you have Dirac type of situation where you harvest spin and orbital correlation. Dirac equation was given to actually explain spin and orbital correlations, and there are various type of things like spin transfer, as you know, happen, spin accumulation happen. Actually, there is a spin Hall effect also, in addition to you might have seen in semiconductor physics in your laboratory at master level. You have the Hall effect experiment where you accumulate holes and electrons in one semiconductor. Similarly, there are many designs where you can also accumulate spins with spin up and spin down conditions. Okay, so that is called spin accumulation and spin Hall effect. Then there are spin damping, that is again a damping function with respect to spiral magnets. Then you have spin resonance. I have already shown you what is it, and There can be 3D structures, and of course, because it is very small size, definitely you have to understand there are quantum phenomena involved, and there is a spin exchange at the interface. So this all happens, as I showed you earlier, this figure. This all happens because originally it is coming from electron, spin and charge both. Okay, and like spin can generate a spin momentum, orbital motion can generate orbital momentum, and these two correlation produce this direct type of materials. So there is another thing now. These are the materials which can be used for spintronics, but there should be some way. You see, you connect contacts, wires. Okay, they are non-magnetic materials. So how to inject spin polarized current? How to generate spin polarized current there, and how to carry it forward in circuits, right? So there are variety of other mechanisms which are available to do so. I have given one example here. Most common method is injecting polarized spin current from ferromagnetic metallic conductor to a non-magnetic material, and then it carries the spin forward. If it scatters more, definitely you lose it. So generally they are thin non-magnetic materials. And here I have shown you normal Seebeck effect, which you all know what happens when you have a temperature gradient and how electrons can move with thermal gradient. Now here in this case, what is it? You have a magnetized magnetic material here with this kind of spin alignment in the layer. Beneath that you have non-magnetic material. This is ferromagnetic, this is non-magnetic. Now you have a temperature gradient given here from high to low. Okay, so because of that, the current will pass from charge carriers will, because of heat difference, will go here from top layer to bottom layer, and they turn together here with the same spin alignment as the magnetic layer. See, here we have not used anywhere external magnetic field. It is directly working on the electron passing through the layer, so power consumption is again low. So this can be actually harvested again to induce spin polarized current in a non-magnetic layer. There are other phenomena like mechanical rotations, geometrical phases where you can do it. Thermal gradient we have seen here. There can be spin band splitting. That is like we will see one example of spin band, different bands like semiconducting and metallic band in the same material. Then you can have optics, to play with it. You can have electric field applied and manipulate the spin polarized current and pass it to the non-magnetic materials and all. So as an example, till now you have seen many applications and many terminology and different phenomena, and these are just a sample. Okay, all this together is just clubbed together for your understanding, but there are many designs possible, variety of things are available, and many different quantum phenomena associated with that. If you go into details, I mean, I have always given some references here, you can refer to that. Now, we were interested more in double perovskites because they are quite promising for spintronic applications. So let me explain you how. If you take a perovskite material like perovskite means CaTiO3, originally it was having some kind of structure as shown here. The same structure, whatever oxide acquires, we call it a perovskite like structure. Okay, so generally it is called AbO3 type. This is like LaMnO3 we have shown. I have shown you earlier the same structure here, and you have octahedrals, different octahedra shown here, and in middle you have A site. Now, if you want to double this unit cell, so what you do is you have SR2 sitting here as green sphere, Fe and Mo as alternating unit cell on the top of it. So here you have a double perovskite like situation in the structure. So you have one A site ion that is both actually having SR2 occupying this S site, but your B site is different. It can be FeMO or some other chromium and MO. So these kind of situation is possible. So these B sites you can generally play with. Generally 3D metal ions occupy B and B prime sites, and then oxygen 6. So if it is perfectly alternate position, you call it double perovskite because the unit cell is doubled. So why they are important now? So basically, spintronics applications, because of their half metallic nature, we'll see half metallic later on. Then they have magnetodielectric properties. They have magneto-capacitive properties. That means on application of magnetic fields, dielectric constant can change or capacitance can change. Multiferroicity is there. Many of you know what is multiferroic. There are multiple orders present, magnetic and electronic. Then you call it multiferroic, and there are other things also involved where you can manipulate the one magnetic property can be manipulated by application of electric field and vice versa. Okay, in multiferroic materials. Now, there are two transition metal ions in the double perovskites. So you can play with the metal ions and enhance the versatility and complexity of the properties, and you can modify the properties and tailor them for your requirement, you see. And now, see, this is a complex scenario, if you see, because this single perovskite having just one S site which is quite large ion, then you have small ion and oxygen ion. So they are all different size generally. It doesn't switch the position. But in case of double perovskites, I'll show you. It is possible they switch the position and complexity gets involved here. So these investigations, they get intensified after the discovery of a large magnetoresistive effect at low magnetic field at room temperature. Okay, their transition temperature is around 410 Kelvin, and that is mainly observed in SR2 FeMnO6. So at room temperature with very low magnetic field, you can see magnetoresistive effects. That is the idea. Since that discovery in 1998, which was produced in this paper produced by Kobayashi et al. And published in Nature in 1998. After that, you see the rise in the research papers year by year. For if I search using double perovskites in Scopus, so now you see in 2023, it's like 1,000 papers published with keyword double perovskites. There can be many more. I just search by using Scopus here, and whatever is shown, I'm showing here. So it's consistently rising, and you can see, you can predict that it's going to rise only because of this rise in the area of spintronics and their technology. So these double perovskites generally having this kind of composition, where A site is occupied by strontium, then iron, molybdenum, and oxygen 6. Generally, strontium is studied a lot. There are few papers also where you replace strontium with calcium and barium. So there is some table given here to understand there are some half metallic compounds, and there are some not clearly spin polarized state is achieved here, and they are monoclinic in structure. Magnetic order can be achieved at different temperatures, so mostly they are above room temperature, right? That is why they are studied, because at room temperature, if you want to use spintronic devices, you have to have magnetic ordering above room temperature, and as you decrease the temperature, it will be kind of in the same magnetic state, whatever it is achieved. There are no structural transitions involved, so it is more desirable. Now you have various combinations studied and published. This is taken from a review article, this figure, and TC is plotted on y-axis, how it varies with different doping level at chromium molybdenum site. It is shown here, and here our interest lies here in FeMO based double perovskites. It's slightly above, actually quite high TC here, and more of it is a flexible structure. It is a flexible perovskite structure. You see, it can accommodate variety of 3D metal ions. That is more interesting. So degrees of freedom at lattice level is quite high, and without losing its phase diagram, it can actually change the transition temperature slightly here and there. So you can harvest this situation for benefit of your requirement, right? Uh, okay, so as I told you, they have low field magnetoresistance and half metallicity. What is half metallic? That is shown here slightly. This is a picture taken from Kobayashi et al. Published in Nature. You have density of straight shown here for SR2 FeMO6 type of double perovskite, and you see there is no overlapping when this T2G MO orbital, and this is FeEG orbital. So in such case where there are no overlapping, it is generally spin up channel, so it is creating a gap here. It is semiconducting channel. There can be a spin down states and overlapping of these two orbitals. Okay, T2G of MO and Fe, and then it becomes metallic because there is no gap. So you see there are two spin channels, spin up channel and spin down channel, if it is perfectly ordered in alternate fashion. So spin up having a gap is semiconducting channel. Spin down having overlapping orbitals is a metallic channel. Okay, so when you conduct the charge, there are two channels operating simultaneously. That we'll see now further. So what are the features, different features of this double perovskite? So you have a high Curie temperature, half metallicity, saturation, magnetization of this value, and these are the applications of this material. And most important feature is it is predicted to have 100% spin polarized state at the ground state because of these two channels, having gap, one without gap. Because there are similar size of molybdenum and Fe ions, you also have this problem of anti-site disorder in these materials. By the way, how much time I may have? It looks like I have taken more time. Hello? 5-10 minutes. Okay, then maybe I'll skip few things. Here I would like to show you that see, when you do thin film deposition, generally thin film deposition of double perovskite is not so easy. Only PLD ground films are shown generally to have half metallic nature and perfect cation ordering. Okay, so now one important feature which we observed in our laboratory is that when you vary the background gas pressure from low to high, you can see the impurities coming up. So what we observed is that it is better to have vacuum and deposit the films. So that kind of film having very high cation ordering at B site. So that was published in magnetochemistry recently, and it was selected for a special collection. And we could see that as we change the gas pressure, the highest cation order was observed only in vacuum. Okay, so later on whatever we deposited, we went ahead with vacuum only. So these kind of films having again different types of gas pressure, maximum was always achieved in vacuum is shown here by highest magnetization. Now you may ask me why highest magnetization shows that it is a high cation order. The reason being FeO-MO exchange is ferrimagnetic in nature. Ferrimagnetic means one sublattice having up spin, other having down but unequal spin. Okay, so compensating spin is smaller in size. So you have some net magnetization, positive magnetization. Okay, so this situation arises when you have alternate FeO-MO arrangement only. Otherwise, it is antiferromagnetic or paramagnetic, which does not contribute so much to the magnetization. So it is a clear indication, higher the magnetization, then higher the cation order. So that we have observed clearly in our thin films. And also we have another feature added here in addition to vacuum. If you choose your crystal very wisely, 100 oriented or 111 oriented, depending on that you can also control your cation order, and as you control the cation order, the half metallicity is intact, and you can have more and more spin polarization in this material. So that is possible to achieve when you have more and more alignment is possible when you have 111 oriented 111 crystallographic orientation in the beneath the substrate beneath the thin film. That also we have proved actually efficiently using variety of experiments, including terahertz time domain spectroscopy and Raman spectroscopy. In Raman spectroscopy, we have done temperature dependent Raman spectroscopy of selected thin films having very good cation ordering, and we found that this variation in Raman shift can be actually fitted to Balkanski model, and that the enharmonicity coefficient in Balkanski model can actually help to understand whether there is any coupling between spin and phonon. So spin phonon dynamics are coupled can be seen in our results very clearly, because you can see there are drastic deviations from the trends near transition temperature. So this is the first such experimental observation found in double perovskite thin films, which was published in New Journal of Physics recently. Earlier, no such spin phonon coupling has been actually reported in bulk of these materials. Only thin films are showing this kind of coupling, and we could experimentally observe by various techniques. Okay. So to conclude, we have this is the conclusion mainly on our results. They are highly this double perovskite thin films are highly sensitive for deposition parameters, particularly to the background gas pressure. We have successfully produced nice films in actually vacuum condition. Then we have done various experiments and modified as per the different deposition conditions and your substrate orientation. And we have experimentally demonstrated that 111 orientation is the best to get the cation order. And our results, all results, corroborate very well to show that there is a spin phonon coupling in these thin films, which is absent in their bulk counterparts. I would like to acknowledge BRNS and SCRB for funding these projects, and DST FIST project of our physics department at IIT Indore, DST, under which we have procured a Raman spectrometer. I would like to acknowledge my two students, Dr. Ekta Yadav and Mr. Ketan Naule here, who have this is the PhD work of these two students I have shown here, and presently Ekta is a postdoctoral researcher at IISc Bangalore. This is my research group at IIT Indore. Some alumni are present here. He's working in NICER Bhopal at present, and she's an assistant professor in a private college in Indore. So thank you all. Any questions?
Any questions from audience? And you can also ask the question from chat also.
Thank you so much, ma'am, for the nice talk. I have a question from slide 8, where you've shown that GMR is decreasing with increase in chromium thickness.
May I know who is this asking?
I'm a PhD scholar from DAV, ma'am. Devi Ahalya Vishwavidyalaya, Indore.
Right. You are just in neighborhood, right?
Yes, ma'am. So
Isn't it?
here
Yeah. Tell me.
you
Tell
just
me.
explained, probably it's slide number 7, and you just explained
Okay.
that with increase in distance, the RKKY interactions, they are damped, and hence the this MR is decreasing with increase in chromium thickness. Uh, Hello.
Hello. Hello, madam. Hello. Hello. I think some technical problem. Madam has left. Anyone? Yeah. Wait for a few minutes, please. Yes, madam.
Hello, there was some problem. My battery was drained. So, what was the question?
Ma'am, the question was that since you explained that in
Yeah,
RKKY
damping,
interactions,
damping.
yeah,
Uh,
the damping was happening. So may I know, may you please elaborate more that how with increase in distance the damping is taking, why the ferromagnetic interactions are damping?
because see, this is indirect exchange. Okay, it is not direct exchange. So this actually happens in certain materials where spins are talking at far distance. So spin is carried by electron, as you know. I mean, electron having a spin up position somewhere away interacts with the other electron via the current. Okay, so this distance is actually oscillatory in nature. The Fermi surface having the actually diameter as you change the spheres, Fermi surface having, if you assume it is spherical surface, so as you change the diameter, it has oscillatory nature. There is a lot of theory behind it actually.
So the distance
So
we are talking, that is the diameter of Fermi surface.
this is, I'm talking about a bulk material. RKKY interaction is present also in layers and bulk.
Yeah. So here with increase in the chromium thickness as such,
No, here it is. See, chromium and Fe having exchange interactions,
yeah,
right? So
yes,
there
ma'am.
are two types of GMR materials we should know. One is that in neighborhood you have direct spin exchange interaction. That is also a GMR thing. Another, the first discovery which was made, that was about Fe and chromium. Okay,
Yes.
so that was not explained earlier. Later on, it was found out that there are RKKY interactions also present in these layers.
Okay. Okay, ma'am. Thank you. One another thing is there that generally it is found that the magnitude of TMR is higher as compared to the magnitude of GMR. So may I know the reason for that?
Magnitude of
TMR,
CMR.
TMR, tunneling magnetoresistance magnitude is higher than giant magnetoresistance. So
Hmm?
may I know the reason for that?
You have observed it somewhere?
Yeah, I mean, generally in papers it is written that in TMR we have an insulating layer in between, and
Yeah.
in GMR we have a magnetic layer in between. So,
Yeah.
metallic layer, sorry. So, what causes basically the
See, this
magnitude of TMR?
tunneling is possible in many different devices. So, I mean, it depends on the material and the special layer thickness and all. So, maybe it is generally observed that TMR having higher magnetoresistance, but GMR is also very huge change in the magnetoresistance. But recently, many different designs are possible to get magnetoresistance, positive as well as negative.
Okay, so it cannot be generalized that
We
PMR
cannot
has.
plainly say that something is just higher just because it is this way it is happening.
Okay.
Depends on variety, how you have deposited the layers, what is the scattering rate, how many impurities are there, whether the interface is sharp or not. Depends on many different parameters.
Fine, fine. Okay.
You can
Thank you
just
so much.
plainly cannot compare,
Thank you, ma'am.
Any question from audience?
There is some question about ESR, I think somebody asked.
Anyone?
Is there availability of electron spin resonance? See, we have one user facility, central user facility in IIT Indore. So those of you who are interested to avail that facility, you can check our website, Sophisticated Instrumentation Center at IIT Indore. And many facilities are listed here. On payment basis, you can actually make measurements.
Okay.
Any questions?
No question. Then, madam, I would like to thank you very much for giving a nice talk.
Okay, thanks. Yeah,
And
thanks.
now
So I'm leaving.
okay. Now I invite our another speakers, Dr. Mukesh Ranjan sir. Now Mukesh Ranjan sir is a scientist officer G at Institute for Plasma Research IPR Gandhinagar, well-known institutes. He had did his PhD, MTech and MSc. MSc from IIT Roorkee, MTech from IIT Kanpur, and PhD from Germany. He is the awardees and fellowships of different BAE SSPS, Young Scientist, Young Researcher Award, based oral presentations, and many invited talks delivered at as a national and international conference. He has published more than 100 publications in reputed journal and also 6 books, chapters, and most important, 4 patents on his name. Sir has already completed 40 research R&D projects, research and development projects like ISRO, DST, DAE, J&J, IITs, universities, CSIR, etc. all from these bodies. Under his guidance, 5 students has already completed PhD and 3 are pursuing. And several postdoctorate IPR Inspire Fellow also. Sir, on behalf of the Vigyan Yatra, I invite you to deliver a talk. The title of the talk is Arsening Plasmas for Societal Applications. Interesting topic. Sir, I invite you. Please. Hello.
Hello, am I audible now?
Yeah.
Okay. Is my presentation is visible?
No. Yeah.
So thank you, Professor Pankaj, for your kind introduction, and thank you, the organizer, Professor Nikesh and Dr. Piyush Solanki, for inviting me and arranging such a nice long series of good presentation for including various experts. So, am I audible now, students?
Yes, sir.
And my slide is also visible. Okay, good. So my topic is slightly different than what we have been hearing from the past couple of days. So basically, the talks earlier were mainly focused about the materials, their properties, and their characterization. Basically, I'm also a material scientist, but today I'm going to show you what actually in my institute people are doing, not specifically what I am doing. So I'm coming from Institute for Plasma Research, and in basically IPR has now 3 campuses. The main campus is very close to Ahmedabad airport, so where the people are working on futuristic fusion related experiment. But we have a division where facilitation center for industrial plasma technologies. Just a minute. Yeah, so facilitation center for industrial plasma technology, as you can see the word industrial plasma. So we supposed to develop a lot of technologies based on plasma and then commercialize it for the societal application. So my talk is basically focused by covering the work done by my various colleagues in different plasma based application. Yeah, so before I start, I would like to introduce you what is plasma. So normally we know about school level physics that there are 3 states of matter. One is solid, liquid, and gas. So in solid, the atoms are very tightly bound. We know different kind of crystal structure like P type, B type, where atoms are arranged, and so they're not free to move. But if you give some additional energy to these atoms, so it become in the liquid state. So in liquid state, still the atoms are bound; they are not free to move, but they're flexible enough so that they can change their shape, but they are still binded together. But if you give some more energy, so that this liquid state become the gaseous state. So and we have a lot of in environment, we have a lot of so many gases, and we are breathing gases through from the atmosphere. So atoms are still so in this state, the atoms remain in the molecule form. They are free to move, but still it is in the neutral form. So all this we have solid state physics understanding, we have liquid and liquid flow understanding, we have gaseous physics understanding. So what is the 4th state? So we know that in atoms, the electrons are revolving around the nucleus. So any nucleus has an electron which is revolving around it. So what happens? So because nucleus is positive, you have protons there, and electron is negative, you have electron charge negative. So overall the molecule is actually remain the charge neutral. So because the charge and the positive charge and the negative charge are equal in number. So that's why in normal atmosphere we have because of this neutralization of charge, you have a neutral atoms available. But if you give some energy to this outermost electron, what will happen? This electron will comes out. So what will remain? You have a energy deficient ions. Electron deficient atoms, we call it as an ion. So ions is basically you have less of 1 or 2 less number of electrons. So this state is, if you somehow keep on giving the energy, we call it this state as the plasma state. So as I said, electron will like to move the ions. So electron is negative and ions is positive. So they will like to meet each other. So the moment you stop the energy, electron will immediately meet the ions, and then it will make it neutral. So to produce any kind of plasma, you need energy. So this is what is shown in the 4th image. So it's a combination of neutral gas, positive ions, and electrons. So that's why the physics in this case is very much complex. So you not only apply the electrodynamics, you also apply the fluid dynamics, gaseous physics. So many physics together they modified. So that's the reason the plasma is popularly known as the 4th state of matter, where the electrons and ions and neutrons are present. Because if charge state, you have ions and the electrons, you can control them by applying some external electric or magnetic fields. Normally in neutrals, you cannot apply any field because they are charge neutral. But in case of plasma, because you have a charged particle, you can apply some potential to the charged particle, and then you can change their energy, you can change their movement. So this has given birth to many applications. Some day-to-day life examples of some plasma you can see here. So like in the rainy season, you see a lot of lightning is happening. So what is this lightning? Is a kind of plasma only. So a lot of charge is actually accumulated on the clouds, and it's try to find some localized ground. So any charge, like you see in spark plug, when you are inserting your mobile charger in the socket, you see some kind of arcing is happening there. So whenever you have some charge accumulation, it will try to discharge itself through some grounding. So in this case, the neutral molecules available in the atmosphere, they get ionized because of this high electric field, and then they make this kind of plasma. So lightning is a kind of plasma. The gas burner you see at your home, so you ignite it with some lighter, you give some energy, and then it self-sustained to make this kind of weakly ionized plasma. The third picture you have shown is the ash which is generated inside the cigarette. It's also an example of plasma. The sun which is continuously giving us energy since several years, and it will keep on giving you the energy based on the concept of fusion. It's an also example of plasma. This is a decorative item which you will normally gift to the people. So it's a kind of plasma where in the center you have an electrode, and the moment you touch it, you make the connection to the ground, and then it makes different kind of sparks at different locations. So this is an also example of plasma. Our tube light at our home is also an example of plasma. So these are some day-to-day life example. One can actually very easily visualize that the gas has a charged particle by doing a simple experiment. Just take a tube plate and then connect it in the lab. You must be having some DC power supply. Just you connect it and put a candle in between them. So what you will see, because this candle is already ionizing the gas coming in contact with the plume of this candle, it will make the gas weakly ionized. So what you will see that the direction of this plume is started shifting in one direction. So ions will move in one direction and electron will move in another direction depending on the charge polarity. So you will see that it is shifting, and if the potential is very high, you will see exactly a kind of arcing what you see in the rainy season. So this kind of simple experiment you can actually perform at home just to visualize that there is a weak plasma available in the candle which you are burning. Another very recent example you can see is that when we kill the mosquitoes at our home. So that is also, we are actually making a short circuit between two electrodes having high potential, and that it burns out, it makes the plasma. Okay, so killing the mosquito by the mosquito net is also kind of plasma only. And the welding process you see is also a kind of plasma only. So these are some examples which I've shown you that in our day-to-day life, we are already using plasma without knowing that actually it is because of the plasma technologies. Normally, if you have seen, I have presented you different kind of example. One is the welding example, where it is actually welding can melt the material. And in some case, actually, you can touch the plasma. So that's the reason plasma is basically divided in two categories. And one is cold plasma, another is second one is the hot plasma. So cold plasma is mainly, what is the cold plasma? Where the electron temperature is much higher than the gas temperature. So normally, if you remember, I used the word weakly ionized. So if you have 100 of atoms and out of those only few are get ionized, then it's a weakly ionized plasma. So in this case, even though the electron temperature is very high, it cannot give the heat to the surface because the heat capacity is depend on the mass. Q is equal to Mn. So if the number density of the ionization is very less, we call this as a weakly ionized plasma, and that comes under the category of cold plasma. So cold plasma has many applications like surface modification, I will discuss later on. Another is the hot plasma, where the electron temperature is roughly equal to the gas temperature and the ionization is very strong. So it also has many applications, so like the waste disposal and metallurgical applications. So my talk will be covering the both type of plasma, the cold plasma and the hot plasma. So what you see here is just an animation of plasma. So plasma, as I said, it's a combination of electron and the ions. So this pink balls actually are the ions, and the sky blue color is the electron, because the mass of the ions is much higher than the mass of the electrons. So what happens the moment you make the plasma and electrons are much more mobile, they immediately see some surface and then lose themselves. So electrons, because they are much more mobile, they lose themselves. Following them, ions will also go to follow the same path, and then they hit the surface. So whenever you emit something, whenever some surface come in the contact of plasma, the ions started bombarding them. Okay, so what you see in this picture is I have given a negative potential, a negative DC power supply connected to some surface. So when this surface is coming in contact with plasma, the ions from the plasma started hitting it. Okay, so in this way, the surface can be modified with the help of plasma. So plasma has many applications in different directions. Like first one is automobile industry. So different kind of coatings, anti-reflecting coating, super hydrophobic coatings, DLC diamond-like coatings are actually used in different parts of automobiles industries. Tokamak is the fusion reactor where people are trying to make energy like the sun is making continuously. So worldwide research, a lot of research is going on, including India, for the tokamaks for the energy generation in as a futuristic project. Third one is the waste disposal, where the energetic plasma torches are used for the waste disposal. Agricultural plasma has many applications in agriculture. So I will touch all this topic one by one while showing you some examples: medical, textile, nanotechnology, and space. So this is the picture of our main institute, where we have two running tokamaks, but the Aditya and SST1, where the tokamak is fusion related research is going on, but I'm working here in Facilitation Center for Industrial Plasma Technology, which is there in Gandhinagar. And some of the fields which are actually we are working here are listed here. So we work on space application, we work on waste disposal, we work on plasma nitrating process, implantation process, we work on plasma-based nanoscience and different industrial coatings and so on. So the first example which I'm going to show you is the plasma technology for the waste disposal. So nowadays, waste is a very big threat for any growing city. So you must have noticed in your cities that all the waste is actually collected from your home, and then it is piling up at the end of the city. And what happens after some time, the city actually get extended, and then some people are actually living very close to the area where all this wastage is actually getting piled up. So it's a big problem for the people who are living very nearby. And you might have seen that actually some smoke is also coming out from this waste, because all these places government is trying to use the incinerations where they actually dump this waste and burn it. So by simply putting either using kerosene oil or by petrol, so the waste is actually burned. And what happened, if some waste is coming from the hospital and it is hazardous, or it is some deadly virus are there in this waste, it can also spread in the nearby slum area. So that's the reason the waste treatment is very important and crucial. And I think the modern city concept, it's a very important key topic which has to be taken care of. So we have developed a plasma-based pyrolysis method. So in this plasma-based pyrolysis method, as compared to the incineration, where they are simply burning in presence of oxygen, in the plasma pyrolysis system, what we have energetic torches. So this is an example of the torch. Just a minute. I think I need to change my pointer. Yeah. So what you see, this is, I hope you are able to see this movie. So this is an energetic plasma torch. So in this plasma pyrolysis system, we have a cabin where you can actually dump your waste, and then that waste actually come in contact with this energetic plasma torch in absence of oxygen. So there is no oxygen. So what happened is this plasma torches, they give extensive energy, and then they chop up the bonds of your polymer waste or your food waste or your medical waste up to the level of molecules. So let us say you have some polymers and you start chopping the bonds. So finally, what will happen? It will release the gases at a molecular level. So whatever hazardous gases they are actually generated in this process, they are actually trapped in the vertical columns, which is shown in this picture, and only the environment-friendly gases are released in the atmosphere. So this system actually there is no dioxin or furans actually released, and it is done in the oxygen-starved atmosphere. So, and plasma has a very nice beauty that it also kills bacteria, viruses, because it also emits UV radiations. So it's a very good, so you are not only actually decomposing your waste, but you are also killing the hazardous or deadly viruses in this process. So, and there is no waste generated later on. So if once you burn something, you actually finally making some kind of ash in a normal burning process. But in this process, you are only making different kind of environment friendly gases. So this system has been developed over a period of time, and Central Pollution Control Board of India has actually given its approval for this plasma pyrolysis system. And these are some in this table. What you can see, there's a comparison that what is Central Pollution Control Board standard talks about, that if you have a carbon monoxide, the limit should be 100 mg per newton meter cube. But all this carbon monoxide, NOx, particulate matter, and dioxin and furans, in our system, they have to be found much lesser than the recommended value. So that's the reason it was by performing several R&D experiments over a period of time, this system was successfully proven to be a very good clean technology for the waste disposal. So such kind of system we have already installed at, so we initially started from a low capacity system like 50 kg per hour, and it was installed in Goa Medical College in 2004, where the 3.5 tons of waste was disposed in 1 year duration. Another system was actually installed in Gift City, Gandhinagar. So in Gift City, actually it's a modern city where if you have a multi-story building and all the floors of the building is actually connected to the plasma pyrolysis system. So whatever waste is actually generated, that is directly going to this plasma pyrolysis system and it decomposes there. So it has an advantage that you don't have to shift your garbage from one place to the another place. Whatever wastage is generated in this building is actually decomposed there itself. So after developing this technology, we have actually transferred the technology to different companies time to time, and they are doing marketing and other improvement in the system time to time. This is a very one latest news where our Prime Minister Narendra Modi. So IPR is actually going to install a very big system in Varanasi. So recently, our Prime Minister has actually inaugurated this site. So this is in this movie you. So in this picture, you can see Director IPR and the scientists who actually developed this. So this site has been finalized in collaboration with Tata Memorial Center, Cancer Research Institute in Varanasi. So site has been finalized, and now I'm going to show you how this plasma pyrolysis system is going to work there. So this is what I've shown that, and this is a very proven technology, and our institute get several awards time to time for developing this technology. And I hope in future several such systems you will see at different places. So with this, now I move to the another technology which is already also developed at our place, which is plasma technology for increasing life of steel components. So steel is actually the main component which is used in industries. Any kind of tools is made of steels only. So we have developed a process which is known as the plasma nitrating process. So in this plasma nitrating process, what we actually do, if you have an SS component, you put that component inside the plasma and then give some negative potential to it. So because SS is conducting, and once you are connecting it to the negative power supply, so what will happen? It will attract the nitrogen ions. So this nitrogen ions, they will actually diffuse inside the layer of your steel. So what will happen, because we know steel has a problem that if something made of steel is lying outside, it will very easily get the rusting. So after some time, you will see that the color is changing, will become reddish. So the silver oxide is started forming. Also, if a tool is used very frequently, we want that industry should want that the lifetime of this component should be much more. So that's the reason this plasma nitrating process is very effective. The nitrogen ions, they diffuse inside the steel up to hundreds of microns, depending on the dose you are giving, and then they protect it from the they make it anti-corrosive resistive, and then they increase the hardening of this steel component. So I'm going to show you a movie again, how the plasma nitrating process is actually done. So you can enjoy this movie. So you can see in this system that first we clean the samples and then they mounted in a chamber. So these are some tools which are hanging and going to start the plasma nitrating process. So we have some big size. This is a smaller movie chamber. I will show you that we are regularly doing the job shop for industry people. So we have very big size plasma nitrating chamber available with us. So after mounting it, we have in-house developed, indigenously developed power supplies, and all the database for different kind of steels is available with us. So time to time, students are also doing PhD work for doing the plasma nitrating process. So even though it's a commercially available process, but research is still going on to improve it further. So now you can see that the plasma nitrating process is actually going on. So whenever you see the pinkish color, that is a representation of plasma. Okay, so now you see these tools are now getting plasma nitrate, and this process is keep on going day and night. So it has to be very stable, and so initially you see some kind of flickering is happening. That is the surface cleaning process is going on, and then after that the nitrogen started going deep inside the layer. So these are some, you can see based on the size of these tools, you can see how the different kind of variety of plasma the tools can be perform plasma nitrating. It is not a shape dependent process. So whatever you immerse inside the plasma, it will get plasma nitrated from all the direction and very homogeneously. This is another big reactor where you can see the plasma nitrating process is actually going on industry bearings. You can see. So there is another competitive process known as the chemical nitrating. The difference between chemical nitrating and the plasma nitrating is that in chemical, finally you are making some kind of waste of chemicals. So after doing the nitrating process, this chemical actually has to be decomposed again. So it's a big problem if you are dealing with regular basis on large component. So that's the reason plasma nitrating is a very clean way of doing plasma nitrating process and very effective. And it is performed, as I said, it is not a shape dependent phenomenon. It's because plasma has the beauty of whatever you immerse inside the plasma distributed very homogeneously in the surroundings. This is an example of plasma cleaning process on valves. So plasma is known as a very good cleaner because if you know, when you go to market for repairing, let us say if there's a puncture in your tire tube and then you're going to the market, so what they do, they simply clean your surface by rubbing a emery paper. So emery paper has a small glass particle on the surface. So when you rub it, you are actually cleaning the surface to make it more reactive. You are releasing the bonds. So when you have a sandpaper, these glass particles actually are separated either by fraction of millimeters or some hundreds of microns. But once you are doing the same process by plasma, you are actually bombarding the energetic ions on the surface. So you are doing the atomic cleaning. So emery paper is doing the cleaning at a micron scale or millimeter scale, but once you immerse something inside the plasma, you are actually doing the cleaning at an atomic scale. So that's the reason plasma is a very good cleaner. So there's a company which is the largest manufacturer of this kind of valves. So in all the tire tubes, you have a brass to rubber bonding. This is what you see on your screen. So this brass to rubber bonding has to be done in a very clean manner. So this company actually, they approached us whether it can be done with the help of plasma. So we developed a very big chamber where the thousands of such glass to burners can be treated. And you can see that this treatment is going on. This process to you maybe appear to similar to like the plasma nitrating process, but the difference is in this case you have an argon plasma, not the nitrogen plasma. Nitrogen is a reactive gas, but argon is an inert gas. So argon will not react with your surface, but it will actually bombard your surface. So whenever you have argon plasma, it try to remove some material from the surface. So you put some potential on this whatever object you put inside the plasma and make argon plasma, and then this energetic argon ions they will clean the surface. So this technology we have transferred to this company MS Titan Valve in Mysore. So they are regularly using it, and they have made several such more bigger system of this similar kind. This is what I was showing you, that the plasma is doing the cleaning at an atomic level. Another plasma-based application. Plasma has many applications in the health sector. Some of them they are actually listed here, which we are working in our institute. we are doing the cancer treatment, we are doing the skin treatment, we are doing the blood coagulation, tooth cleaning, sterilization, and pesticide removal. So we have actually developed a touchable plasma. So till now, whatever I was showing you, either you have seen a plasma inside a vacuum system, or in the plasma pyrolysis system, the energetic torches, the energy of the heat was so much generated that you cannot touch it, because that was used for the pyrolysis purpose. But now, very recently, a touchable plasma jet has been developed, which is shown in this movie. You can see, and then we'll discuss about it. So what you will see, this is a fancy plasma torch, which is very handy. And my friend actually showing you that he's putting this plasma plume on his skin, and you can see that he's not getting any shock and he's not getting any heat generated on the surface. So it's a touchable plasma. So touchable plasma has now come up with the many applications, which I actually discussed earlier, that it is used in as a health treatment. So we are using this, just a minute, with the help of Tata Memorial Cancer Research Institute. We are actually doing a cancer treatment on hamster buccal pouch cancer. So we have given this pencil plasma jet to different institutes like AIMS New Delhi and Tata Memorial Center Mumbai, and several other research institutes who are actually looking at the applications of this pencil plasma jet. So in this case, what you see that a hamster, they artificially generate a oral cancer in his mouth, and then they systematically perform by taking approval from the department that they are actually treating the buccal pouch cancer. And we have seen that after the treatment of 1 day, 3 day, 5 days, that slowly this cancer actually, the tumor actually started shrinking. You can see that after the 4th treatment and on day 8, it becomes black, and then it falls down from the buccal pouch. So based on doing one experiment, we cannot conclude. So we actually, since last several years, we are trying to do this kind of experiment on different kind of mouse, because sometimes it also depends on the immunity of the mouse. So continuously we are doing experiments. So getting ethical permission of any device to be approved is take a lot of time, lot of trials. So at the moment, this kind of trials are going on not only in India but worldwide, are going on different mouse, and then people are reporting the result that in certain cases which kind of tank cancer is actually showing the positive result of the treatment. Another application of this pencil plasma jet is that it can treat a kind of fungal infection which is there in the West. A lot of laborers actually, they were getting this Tina Cruces disease. So this looks like a eczema. So earlier they were going to the hospital, and then they're supposed to buy a very expensive paste to be put on this skin disease, and after certain period it was again coming back. So with the treatment of this pencil plasma jet, we have successfully seen that after few trial, this slowly actually it is going, and then and it is permanently going, and then they don't have to come back again for the treatment. So earlier, when they were doing it using some cream or some paste, it was only applied on the surface. So it was not killing the fungal infection deep inside the skin. But because of this pencil plasma jet, the ions and the radicals, they can actually go and penetrate inside the pores of the skin. And then it is more effectively found as compared to the other treatment. So this kind of study actually are also going on currently. And this so pencil plasma jet is also there report that people have used it for the tooth cleaning. We have some sulfur deposition on our teeth which can make it yellowish. So maybe hopefully in future you will see that the dentists are also using pencil plasma jet. So we are already doing some collaborative work with different dental institutes to see whether the dental cleaning can be also possible with this pencil plasma jet. It's a very good blood coagulation. So whenever you have met somebody has accident, so they are already report that if you use the pencil plasma jet, it coagulates your blood very fast. So there's a possibility that this kind of pencil plasma torch can be kept in 108 emergency emergency vehicle, so that the doctor can, if there's a lot of blood is coming out from the wound, so it can be treated very fast, and then it can stop the blood flow so that the patient can be saved. So even if you see on the YouTube, you will see that in the doctors, they are using it after doing the operation to stop the blood. They actually putting using this kind of pencil plasma torches to stop the blood after the operation. This kind of pencil plasma torch, we have also shown that they can use to clean the vegetables. They actually, if there's a pesticide available on the surface, so this kind of pencil plasma torch actually put. So we have made a shower of this pencil plasma torch, and then with the help of labs, we have tested that once you treat it with the pencil plasma jet, the molecule of the pesticide actually moves away from the surface, and then it is perfectly clean. So there's a possibility that you will have a shower kind of like pencil plasma jet in your microwave oven, then you run it, and then it will make it pesticide free. So this kind of research is also going on in our institute. Yeah. Another very good application of plasma is the plasma installation. So traditionally, when we go to any hospital, the doctors are actually using autoclave for killing the bacteria on the surface. So normally they put their Caesar, their other equipment which are used for the operation inside the autoclave, and then hot water is generated. Basically, steam is generated, which is actually killing the bacteria. But still, there are several bacteria which are able to sustain at such a high temperature also. So that's the reason plasma has proven to be a better plasma installation, because it generates not only the energetic ions or radicals, but it also releases the UV. So it's a combination of various things. So there's various reports. People have used different kind of plasmas for killing very well-known bacteria. Some of them, they are listed here. So, and there is a 6-log reduction we have seen in our institute, that it is actually in collaboration with Nirma University. We are doing this kind of experiment. So this is an indigenously developed plasma installation system, where initially we started for making normal DC plasma, then microwave plasma, and different kind of plasma we are using, and their effectiveness as a plasma installation. So plasma installation is also already in industries. They are selling commercially this kind of system, and they're very, very expensive. So like Johnson & Johnson, they are selling plasma based installation, and some of the hospital in India already they have it. So we have also developed this indigenous plasma installation system at IPR, and then technology of this about to be transferred. Plasma is, as I said, has application in agriculture. So if you have a seed, normally the seed takes some time for the germination. Okay, so there are reported available, and then we have, this is our own work where we have seen that some seeds, when we treat them with the plasma, what happened that it removed the upper shell of the seed, and then it make its surface hydrophilic. So it absorbs much more vapor or much more water or the other content, so it grows faster. So this, you can see the SEM images of the seed before and after treatment. So untreated seed is very smooth, and that plasma treated seed has some kind of roughness generated on the surface. So once you have a surface roughness generated, the surface area is increased, and then it is much more easily absorb the water from different sides, and that's how the seed grows faster. So we are working with Anand Agriculture University. We have supplied a system to them also, and we have a system at our institute, because seed germination is a process where we have to see the statistics. So we treat the thousands of seeds, and then on different kind of seeds we treat time to time, and then see how fast they germinate. So you have to every time wait for several days and months when the seed started germinating, and then make a comparison that what was the optimized time for the plasma treatment, and how the seed germination is actually effective in particular type of seed, but it is not effective for the another kind of seed. So this is a broad area where a lot of data has to be generated for different kind of seeds, how the plasma technology can be helpful for the seed germination. But till now we have found that it is very promising, and already worldwide a lot of research is also going on this topic. Another very recent advantage of plasma technology is the plasma activated water. So plasma activated water is basically you have energetic plasma torch and you immerse it inside the water. So this is what you can see in this movie. So it's in this beaker you have a water, and then this plasma plume is actually touching the water. So this is known as the plasma activated water. So the beauty of this plasma activated water is actually it's kind of amrit, I will say. So what you see on the screen is the tomato. So naturally, if you see that fruits or vegetable after certain period they started shrinking, so they no longer remain the fresh. So either you have to send it to some cold storage for storing them for a longer period. So if you wash this tree, this fruit or this tomato with the plasma activated water, you will see that the lifetime of this of the fruit and the vegetable actually increase. So this tomato, you can see a comparison that the first tomato is still remain the same after several days, but the second tomato actually started shrinking. So this plasma activated water also is a very good alternative to pesticide. It grows your plant very fast. It kills the bacteria, fungi, and microorganisms available which are there on the surface, which are responsible for the sinking of the skin, and it's very good for many applications. So basically, what it's doing just above the surface is making different radicals, which are actually after forming they actually immerse inside the water. So some of them are the NOx, nitrogen oxide, some of them are the oxygen radicals, and hydrogen peroxide radicals are generated, which actually remain inside the water for a longer period. So it also works as a urea. So some example I have shown here. So first, these are the SEM images you can see. So how this aeruginosa bacteria actually can be killed if you wash it with the plasma activated water. So the first image is the normal bacteria, and second one is after plasma treatment. It ruptured their surfaces and then finally killed them. The bottom example you can see is the plasma activated water used for the plant enhancement. So first one is normally normal water was given to the first plant, and in second case plasma activated water given. So you can see that the second and third plant grows faster as compared to the first plant. So this work in this case as a alternative of urea. So you don't have to give the chemicals to your plant. Just put some plasma activated water to this plant, and then it will grow faster because it's a substitute of giving the nitrogen. So with this, I have shown you that plasma has application in waste disposal using the plasma technology, pyrolysis technology. Plasma has application in industries where the plasma nitrogen process is working. Plasma has a many application in health where the plasma jet is working for different fungal infection treatment, for the cancer treatment. Plasma activated water has a many application. It is working like a sterilizer. It is also working like a urea. And then plasma has application in health science and the equipment are there which can use as a plasma sterilization. So plasma also has an application in textile. Some of the examples are shown here. So we have developed a plasma-based technologies which actually treat the textile. So in this case, what you see, there's an Angora rabbit. Angora rabbit is actually used in Himalayan region, and its hair are very warm. So they are pure. So they make sweater out of it. So the jackets of the soldiers and some of the very expensive sweaters are made of Angora fiber. But the problem with this fiber is it is very smooth. It's very smooth. So it's very difficult to make 100% Angora fiber sweater. So we have developed a atmospheric pressure plasma based system which can be clubbed to inline treatment of the wool. So this is the technology we have supplied to Mantra Technology, Mantra and Inspiron Ahmedabad. So after the plasma treatment, you can see these are the SEM images on the right side. Before treatment, it is very smooth, and after treatment, some nano roughness generated on the surface, and that's make it so. In terms of appearance, there is no change, but in terms of roughness, it's changed. So now, with the help of this plasma treatment, one can make 100% Angora fiber clothes out of it. So it's a very successful technology, and if you see again Google, worldwide people are using plasma-based technologies for treating the textiles. Some of other examples, you might have seen that on Facebook or WhatsApp that some barbers they're actually burning the hairs. So while they're burning the hairs, actually they are making your surface more reactive, basically it's a plasma only. So once you have a plasma treated here, you can see that the dye is absorbed much more as compared to the untreated one. So plasma actually basically make your surface more active, and it removes the contamination from your surface, and that helps the dye molecules to spread more homogeneously on the surface and then deep inside. And then because the roughness is also increased the surface area, so the dye is actually absorbed much more as compared to the untreated sample. So this is another example that if you treat the textile or anything from plasma, its surface is much more reactive, and so it can absorb the dye very easily. Another example is what you see here, this blue color bonds, is that khadi treatment. So khadi actually has a natural wax on the surface, which doesn't allow it to absorb any dye. So that's the reason khadi is not only coming in normally in the one color only. Okay, so if you treat the khadi with plasma, you can see that it absorbs the color very easily. So what plasma does, it actually remove the wax from the surface, and then it's easily able to absorb different kind of dyes. So with this experiment, actually one can, even with the khadi can be used for different colors. Another example of plasma torches can be used for making the monkey wash kind of design on the surface. So you can simply computer program your plasma torch and then write any different designs on the surface. So this is an example shown here is the plasma torch color fading of denim. So if you, depending on the time of exposure on the surface, as I said that it removes the color, it helps to absorb the color, but it also helps to remove the color from the surface, depending on the dose or energy you are choosing. So by this, you can write different structure on the surface. So plasma is also plasma-based technologies are explored for different application of in textile. Now this is my favorite topic, plasma nanotechnology. So we know that naturally the lotus leaf is naturally a super hydrophobic in nature. So if you see the lotus leaf in high resolution, so you will see that it has nano and micron size structure on the surface, which actually doesn't allow the water droplet actually wet on the surface. And because of this nanostructure formation, the air trap inside this structure, and it doesn't allow water droplet to wet. So this kind of natural example you can see in many other cases. The another is the wings of a bee. You can see it has a nanostructures. So if you are artificially able to make nanostructure on the surface, you can actually make, in principle, you can make any surface as super hydrophobic or hydrophobic in nature. So the similar experiment we have done in our lab. So this is an example where we have very nicely controlled the water droplet on the polymer surface. So below you see the SEM images. So initially it has some roughness, and this is an example of Teflon. So Teflon is by nature, it's hydrophobic in nature, and the water contact angle is around 100 degrees C. But if you treat it with plasma, it can make some nanostructures like it is on the lotus leaf. And this nanostructure actually can make this Teflon as super hydrophobic, and the droplet actually started revolving on the surface. So that's the reason why tuning your plasma parameter, you can make surface either hydrophobic or you can make the surface either hydrophilic. So just to show you one movie. So what you can see that this surface is so nicely hydrophobic in nature that even the droplet, when it is falling, it is rolling very fast. And when we try to touch the surface, the droplet actually started bouncing. It's not going. So simply by making nanostructure on the surface, you can make your surface as super hydrophobic. It has many applications. The first example is the self-cleaning. So now you have seen that nowadays people are installing solar panel on their rooftop, and there's a lot of problem of dust accumulation. So when you have a dust accumulation on the surface, you need to wash it. Okay, so you might have seen that people are using shower to wash their solar panels. So but if the fine dust is very sticky. Okay, so if you have a top layer which is transparent, and it has a phenomena of nanostructure of super hydrophobicity on the surface. So when you wash it, you will see that the surface will clean much better than the normal process. So this is what is shown in this movie. So first sample is the treated one, and the second sample is the untreated one. In the first case, you can see that the dust is not sticking to the surface, it is rolling with the water droplet. But in second case, you can see that the droplet is going over the surface, but it is not actually taking away the dust. So that's how this technology can be used for the self-cleaning processes. Another application is if you can make a surface super hydrophobic, you can actually use it for the water condensation experiment. In many cases, there is a requirement that water should keep on moving from one place to another place so that the surface should remain cold enough, like the example of our AC. Okay, so whenever there is a copper pipe or any metallic pipe and it has a low temperature, it will condense the water. So this droplet started forming, and we do not want this droplet should remain there. It should move away. So you can make this surface that super hydrophobic, and then it will actually transport the heat from one place to another place very fast. So I have shown you the example of making the surface as hydrophobic, but there is the requirements at certain places where the surface has to be made at hydrophilic, like the water filter which we have at our home. It has a charcoal filter or the carbon filter. So the requirement is that whenever water is coming in contact, it should move this filter very fast. So what has been observed that this filter is actually, when it is untreated, it is kind of hydrophobic in nature, so it doesn't allow water to go very easily. So you need to push it either putting some force. So you can see the nature is hydrophobic. The droplet is still there, even though it appears to be like a porous one. So it's not absorbing the water. Okay, but when you treat it with plasma, you can see. So plasma treated the filter. You can see it immediately. So the moment the droplet fall on the surface, so plasma can be used to make surface not only hydrophobic and hydrophilic also. So not only by making the nanostructure on the surface, we can also play with the surface chemistry to make surface super hydrophobic. So this is an example of we can make a Teflon using the plasma process. We can make Teflon-like coating on the surface, which is super hydrophobic in nature. So I told you that plasma makes a nanostructure on the surface, and that can actually change the wettability of the surface. So it can make super hydrophobic, it can make super hydrophilic. So this is one example application of the nanopatterns, but it has many other applications. So when the ions are hitting the surface, they can make very well regular structure on the surface. The first example, what you see, the atomic force microscopy image, it can make freely standing nanodot structure. And if it is falling at some angle, the ions, it can make like wavy structure, this kind of patterns. So, and if you see the scale bar is around 200 nanometers, so you have a control of making a regular nanostructure on the surface simply by changing your plasma parameter. Okay, so once we make this kind of pattern on the surface, they can be used as a template for growing nice chains of nanoparticles. So whenever we talk about the nanoparticles, we use some kind of chemical processing where the problem is that the metal, the nanoparticle, they started agglomerated, and there's a lot of residue of the chemicals which are used is remain with those nanoparticles. So they are not pure in the form. So if you pattern your surface with the plasma processing, you can use them as a template to make nicely chains of nanoparticles. So once they are nicely arranged, they have a unique property as compared to the randomly growth nanoparticles. So I'm going to show you an example. So we have developed a technology which is based on this nanopatterning and the combination of nanopatterning and the nanoparticle growth. It is very highly sensitive Raman sensor. If you remember the talk given by yesterday, Professor Dheeraj, he has discussed about the surface enhanced Raman spectroscopy. So surface enhanced Raman spectroscopy talks about that in presence of metal nanoparticle, the sensitivity of Raman signal is increased drastically. So basically it is used for detecting the molecules. So if you have a very, very low concentration of molecule, you cannot detect it with the help of Raman spectroscopy because the intensity is very low and the characteristic peak of Raman is not visible. So this is what is shown in this presentation. The first example is a normal Raman spectra and the intensity is very low and there is no peak visible. Example you see is the rhodamine 6G molecule and very dilute concentration 10 to the power minus 6 molar. And the second one is when you use the same molecule and put a drop of it on top of the metal nanoparticle, you can see some peaks are visible. These are characteristic vibrational modes of the molecule, and this is a Raman spectrum. So this is the beauty of surface enhanced Raman spectroscopy, that it not only increases the intensity and it is able to detect a very, very low concentration of the molecules. So if you have a chains of metal nanoparticles, these are the chains of nanoparticles, So if you have chains of nanoparticles, the signal is much more stronger as compared to randomly distributed nanoparticles. So that's the reason we wanted to have a chains of nanoparticles, because its sensitivity is higher. So why we need it? There's a lot of problem nowadays about the food adulterant. So if you Google it and you see whatever food you are actually taking nowadays, all kind of food actually has been decorated by using the food adulterant. So different kind of dyes, colorful dyes are used so that when you go to the market, the food attract you easily. So it makes it more beautiful, it makes it more juicy, it makes it more sweet. So all kind of non-recommended food adulterant are used in the market, because artificially injections are injected. So there's a problem how to detect them. So with the help of this nano pattern I've shown you earlier, we have developed a sensor. This is known as ASAN, IPR SARS nanosensor. So with the help of handheld Raman spectroscopy, one can put a drop of any juice or any food item you want to detect. So example you can see here, this is the example of turmeric powder. So turmeric powder, they add a methyl yellow dye, which is yellow in color. So that can be detected with the help of this sensor. Chili powder, they add some red color. Watermelon juice, they add rhodamine B dye. And in milk, they add the food melamine. So these are some examples which have shown that it's not easy to detect them at a very low concentration level, but with the help of this developed SARS pattern, you can detect their Raman spectra and then identify that yes, they are not in the pure form, some kind of dyes has been used. So we are making a database of different kind of food adulterant, and this technology is already we have transferred to two Indian companies so that they can sell them to different needy people. We have also detected the different kind of cancer cells. So we are working in collaboration with Tata Memorial Cancer Research Institute. So with the help of nanoparticle, we are able to detect the cancer cells. So Raman spectroscopy is already used to detect the cancers, but once you have metal nanoparticles or these pattern nanoparticles, you can detect them at a very, very low number. Typically, if you need 1 lakh of cells, cancer cell to detect it, now with the help of this nanoparticle arrays, you can detect them in very small number, like 1 or 2 or tens of cells. So it's a again, if you read more about the surface enhanced Raman spectroscopy, you can see that people are exploring it for different dimensions. People are using it for forensic application. People are using it to detect cancer virus. People are cancers of different kinds. People are using it for dengue detection. So wherever there is a problem of detection, this kind of technique is very much useful. Another technology which is developed at our place by Dr. Bala, maybe day after tomorrow you will have a talk from Dr. Bala. So he has developed a technology for making large number of nanopowder for self-cleaning applications. So if you are taking a tea and or coffee and some kind of droplet found on your clothes, so you can take this titanium oxide nanopowder on the surface and then simply stand in the sunlight, and you will see that it is cleaning the surface. So this nanopowder has a beauty that it absorbs the light from the surface and then make the surface reactive and remove the contaminant on the surface. So Dr. Bala will talk more about this technology and in his talk. There are several plasma-based technologies and plasma-based magnetron spectrum system popularly used in different labs. I hope it is there in the Saurashtra University also. So it's a very cheap and economical way of making thin films on the surface. And there are several Indian industries also making this plasma magnetron. So in this example, what you see that we have developed a plasma processing where we are making titanium nitride coating on different component. Or like the one you have seen is the hips joint. So we are working on a project with CSIR where artificial hips joints are developed. So in this hip joint, the requirement is that it should be long lasting. After several cycle of movement, it should have a long lasting. And whatever coating is used should be biocompatible. Okay, so titanium nitride is proven to be a very biocompatible and very hard coating, and that's the reason it is nowadays used for many biomedical application like hip joints, and in your tooth also the screws are made of titanium nitride. So we have successfully developed this titanium nitride coating using the PVD coating. And the second example you see is the metallic coating over a polymer. So if there's a requirement where you want to make your polymer to behave like a metal surface, you can actually coat it with. So we have developed large scale area coaters based on the sputtering concept. So this is the last part of my talk. So plasma has many applications in space. So we are very closely working with different units of Department of Space. These are some of the example I've shown you. So this is a picture of a satellite. So we are doing the experiment which is known as the surface plasma interaction experiment in collaboration with ISRO. We are making the titanium nitride coated bearings for the satellites. We are making the flexible antenna concept for ISRO, and we are also developing working with them for the plasma thrusters. So plasma thrusters are used for pushing the satellite from when they are moving from one orbit to another orbit, so to increase the length of the orbit. So time to time we are getting different plasma weight requirement of the satellites. So I'm touching one by one. So this is what is we develop a flexible antenna concept in collaboration with SAC Ahmedabad. So normally the requirement in satellite is that we want to reduce the weight of the satellite. So normally they were using a metallic reflector, not like so you have a dish antenna at your home which is made of metal. So similar kind of antenna is actually there in the satellite, so which is very bulky. So the requirement is you just need a metallic surface. So they come up with the idea that why don't we make a polymer based antenna? It's flexible also, you can tune it, its diameter, and it's also behave like a metal. So we developed but the requirement was they have to have a coating over a large area like 20 centimeter, 30 centimeter, 1 meter. So we indigenously developed a plasma-based sputtering system for them so that it can coat homogeneously over the polymer surface. Coating a polymer surface is not that straightforward like you do other coatings. So it has to be first the surface has to be cleaned by the plasma process, and then the sputtered material has to deposit on the surfaces. So we successfully developed this flexible antenna for SAC Ahmedabad. This is the polymer surface uncoated, and the second one is the coated one. Another project which was very successful is the development of plasma thrusters. So plasma thruster is again a device which is a kind of plasma gun. So ISRO, different of ISRO units, they actually started working on plasma thrusters several years ago, and it is very crucial because this is not only used to change the orientation and the direction of the satellite, but nowadays it is also used to change the orbit. So like in Mars mission, they were simply firing the plasma thruster to increase the orbit of it, and during the latest moon mission, when it has to land on the surface, this kind of plasma thruster actually balance the force because there is no gravity there. So this plasma thruster, they put equal and opposite force to the satellite so that it can easily change the orientation, and then slowly it can land on the surface. So that's the reason for the space mission plasma thruster is very crucial. So ISRO actually not only we help them to investigate the plasma property of this plasma thruster, but we also help them to develop the materials used in this plasma thruster. So these are some of the electrical probes which are used for characterizing the plasma thruster. Like Faraday cup is very common, Langmuir probe is very common. So this can tell you what is the plasma density, what is the electron temperature, what is the ion energy. These are the basic information when you fire the thruster you need to calculate the thrust produced by the plasma thruster. And bottom are some plots where we actually investigated how the metal is eroding from the surface when we are firing the plasma thruster. So this white color ceramic started eroding. So they wanted to know how much time it will run, for how many hours it will run once it is completely removed. So those kind of experiments are performed at our lab regularly. Another example is space plasma interaction. So when the satellite is going to the lower Earth orbit, there is a low density plasma available there. So this low density plasma actually, when the solar panel is coming in contact to this low density plasma, its surface started charging, and in space there is no ground. So we know that the top surface of the solar panel is dielectric in nature, it's glass. So whenever charge is coming, the charge get accumulated there, it behaves like a capacitor. And the amount of this charge can be so much that it started creating the arc. So if you remember from my very first slide, I was talking about lightning in the winter season. So similar kind of arcing actually happen on the solar panel. So when we launch a satellite, we predict that this satellite is going to work for 10 years, 20 years. But what was observed that in presence of the plasma, the solar panel started damaging. And I can show you the real proof. So you just see this movie. So this solar panel is kept inside the plasma. Just a minute. And you can see that some kind of arcing happening in between the two solar panels. And yeah, so these are the images captured by a very fast CCD camera. So we developed a facility for ISRO to see whether in presence of plasma this kind of arcing happening, and if it is happening, what is the arc duration, where is the prominent location, and is it happening only at one place or it is happening at multiple places. So we did, over a period of time, we generated a lot of database for them and developed a process where the certain solar panel has to be tested in plasma. Whenever they change any design, it has to be tested in plasma. So this kind of experiments are going on in our lab on daily basis. So time to time, whenever they use new materials, whenever they design new circuit, they send their solar panel to IPR and then we do the testing for them. So with this, I have very quickly briefed you about the various plasma-based technologies. And if you see all of these technologies, actually they are not only physicists are working, all these people of all the disciplines, electrical engineer, mechanical engineer, chemical engineer, chemistry people, biology people, textile people, doctors, all of us, because it's an interdisciplinary subject. So many people and many students are time to time working on this, the developed technologies. So this is my final remark, that we invite students to join some of the technologies we are working here and then contribute for the societal application of plasma. Thank you very much for your attention.
Now, session is open for discussion. Any question from audience? Hello.
If you're hesitant to ask now, you can also write me email or get my contact number from Dr. Piyush, or you can write me. So I will be happy
Also,
to
you
answer.
can ask from chat also.
Yeah, let me see.
Hello.
Yeah, I'm ready.
Audience, please. Anyone having question?
Am I audible, sir?
Yeah, please.
Sir, is this plasma torch commercially available or is it in the research phase?
No, it is available commercially. So both the kind of torches I have shown you, both hot plasma and the cold plasma. So we have commercialized them, and we have also transferred the technologies to industries. So most of the cases, the marketing is done by the industries. So we give them the technology and then they further market it. So this technology we have given. So if you have any query, I can connect you to the right person.
Okay, thank you, sir.
Yeah.
Anyone from audience?
Am I audible, sir?
Yeah, Marvashi.
Sir, you have explained about the use of plasma technique for skin curing. Is this process is available for the societal application?
Yeah, so for this particular experiment, we, as I said, that treating the human body needs ethical permission, and getting ethical permission is not very easy. So in this case, what example I have shown, this experiment we have done in Calcutta with after taking approval from hospitals. So it was very successful for them. So skin treatment, yes, it is easily acceptable, plasma based, but doing something inside the body is not easy. So that process, what I told, is easily available. Yeah, it's available.
Okay, sir. Thank you.
Yeah.
Anyone? Please feel free to ask.
So I can read the question from the chat box.
Yeah.
Okay, so I think there are many, so let me explore it first. The cancer treatment, how and what term the plasma torch different better from the recently used proton beam radiotherapy and treatment through linear accelerators? Okay, it's a very good question. So normally, traditionally, even now, the cancer treatment is done using the chemotherapy. So where this kind of proton beam irradiation or other things are used. So in case of plasma, what we have observed that the question always asks that why it is only killing the cancer cell, not the healthy cell. Okay. In the case of chemotherapy, you might have noticed that the immunity goes down. But in case of plasma treatment, because it generates the radicals inside the cancerous tumor. So the NOx, which are generated there, they are so much generated inside the cell that they explode it. And that does not happen in the case of healthy cells. Okay, so that's the reason it was found to be more effective as compared to the other cells. But still, again, plasma treatment for cancer is not yet started as a practice. It is under research only. But worldwide, you see many people are doing, many reports are coming. It is effective, but it is not still implemented. Then let me see another question. So when the high temperature is given to air, it becomes plasma. But then how cold plasma stay? Okay. So this I explained. So in general, because whenever we say plasma, the temperature is very high. Typically in plasma, 1 electron volt is equal to 11,400 degree temperature. But still it is called as cold plasma because the density is very low. If the number of the electrons or number of ions is very high, then only it will be able to transfer the temperature from plasma to the surface. But because their number is very small, you will only feel it, but it cannot burn anything. Okay. I think I have answered all the questions mentioned in the chat box. Pankaj sir. Me? Meantime, you can
Anyone?
ask.
Okay, sir. If there is no question, I say thanks for a nice talk, sir.
Thank you, sir. Thank you. So I think now we can.
Okay,
Yeah.
so moving ahead, now I invite my fellow researcher, Mr. Sangeeta Chawda, to deliver vote of thanks.
Good afternoon to all. Myself, Sangeeta Chawda, PhD Research Scholar at Department of Physics, Saurashtra University, Rajkot. It has been an honor to be a part of this wonderful event. I would like to extend my heartfelt gratitude to all the participants on behalf of Department of Physics, Saurashtra University, Rajkot, Vigyan Gurjari, Gujarat Prant, Unit of Vigyan Bharati, VIBHA, and GUJCOST, Department of Science and Technology under Gujarat Vigyan Sammelan. I am very much thankful to our today's eminent speakers, Professor Krushna Mavani ma'am and Dr. Mukesh Ranjan sir, who has delivered very informative talk. Your thoughts have truly inspired us. I am thankful to our esteemed guest, Professor Indrajit Patel sir. I would like to thank our chief patron, Professor Nilamri Dave ma'am, for always being supportive and encourages us to organizing the informative seminars. I would like to express my appreciation to our patrons and co-patrons, Professor Chaitanya Joshi sir, Professor Girish Bhimani sir, Dr. Narottam Shahu sir, and Dr. R.G. Parmar sir. My sincere thanks to the conveners of Gujarat Vigyan Sammelan, Professor Nikesh Shah sir and Professor P.M. Joshi sir. I am thankful to Professor Pankaj Thakur sir for chairing the session. I am also thankful to event coordinators Dr. Rupal Trivedi ma'am, Dr. David Dhruv sir, and Dr. Piyush Solanki sir. And I am very much thankful to one and all present over here. So at last, I would like to thank the member of press and media for wider publicity and outreach. Thank you once again. We will again meet tomorrow at same time and same platform at 2:15 p.m. Thank you all.
Thank you.